He wanted me to be the pilot that runs the Titanic missions. And I told him I'm not getting in it.
Hard to believe it's already been over a year since the OceanGate Titan disaster, and now we have hearings from the Coast Guard with key witness testimony from people involved, and we've learned a ton. Now, I want to focus this video on the testimony of Tony Nissen, who's the chief engineer of the Titan program. And a lot of what he's had to say is pretty shocking. Some of it we knew, some of it is new. The reason why we're doing this video is because it's really important in engineering, whenever something goes wrong, to learn how to address it, because that's how progress is made. So let's see if we can figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is sponsored by Delete Me. So the early questions are around standards bodies and classification societies.
Would you have been aware if classification societies were ever notified or discussed with for the Titan submersible?
So I know Stockton was in a spat with folks from the class societies. He was annoyed that they wrote letters to him and it was too expensive to class and they didn't want to be part of the project. It was annoying to me. You know, we didn't share data, or they didn't want to be part of it.
It wasn't that they were trying to avoid it. It wasn't like they were deliberately not trying to get it classified. It was just expensive, time consuming, and a lot of this stuff had never really been done before. So they would require huge amounts of testing. And that's a theme that we're gonna go back to here in a minute. One of the really interesting things that he says,
we could 100% engineering wise prevent all traffic accident deaths.
but what would that mean? Probably 2 or 3 hours added to your commute times, right? If every light had some sort of check to make sure that nobody was ever in danger.
We would all be giving up a lot of convenience to do that.
His point is, in engineering, oftentimes we have to make a decision between absolute safety, absolute convenience, and find where's the best balance of the two.
I don't think classing would have prevented this accident.
Airplanes, the FAA, the NTSB have rigorous classification bodies and standards, and we still have plane crashes. And not to mention with situations like the Boeing 737 MAX, where they skirted these regulations, called this new aircraft platform a 737 and got the qualifications to be passed over. Even though the entire aircraft was bigger, the engines were massive, it had to be lifted up, it caused a nose-up attitude in flight that required software to fix it. But anyways, his point is, there's no perfect way of doing anything. The next key point is testing at the Deep Ocean Test Facility in Annapolis, Maryland, something that they were going to do, but ultimately did not.
We wanted to hydrostatically test, so we wanted to fill it with fluid, but there was going to be computers inside because we had to measure data and they needed to isolate that from the water. And the Deep Ocean Test Facility wasn't comfortable with us doing that. I submitted a plan, a request to be able to do this. They came back with, we don't know if we want to do that. This is one of those cases where Stockton got fed up and said, then we're not going. And it was going to push us like another year. Like I couldn't get it done fast enough.
The Deep Ocean Test Facility is exactly where this sort of testing should be taking place. In fact, the US Navy has performed testing of this variety for this very reason, and they did not. And they claimed that because of their instrumentation and computers, the facility had objections to doing a hydrostatic test. But that doesn't really make all that much sense because, again, this vessel, this pressure vessel, one of the largest in the world, is made for exactly this purpose. And as you can see, they support static pressures of up to 12,000 psi, which is plenty. And they even allow for fresh or salt water during their testing. So they could have taken the Titan, put it in there, ran it at 5,500 or 6,000 psi, which is about what they would have seen at 3,800 meters at the Titanic, and done some tests. This is really important because one of the things that you can never fully predict in modeling is how these sorts of systems will fail under pressure and depressurization cycles. Aircraft pressurize and depressurize the cabins to make sure that they can withstand, 10,000 flight hours, whatever the number might be. And the same thing really needs to be happening here. Now, if they were going to devise the Titan to be a one-time use craft, that's different. But we'll get to this here in a minute, why all their countermeasures or their protections that they built in to detect any sort of issues would have been insufficient. This video took a long time to research, and it's amazing just how much data is at our fingertips thanks to the internet. But what about your private personal data? Sadly, it too is equally available online. It's why I've been a member of our sponsor this week, Delete Me, for almost 2 years. Delete Me is a hands-free subscription service that will remove your personal information that's being sold online. And it's not just a one-time scan. Delete Me will constantly monitor the web and remove your data as needed. I just got my 7th quarterly report, and Delete Me scanned over 14,000 listings. The really frustrating part is that my address is one of the most popular things being exposed. Delete Me also announced an exciting expansion of their core service to easily extend protection and peace of mind to anyone you wish to include, because it's not just about you. Privacy online is a family affair. I know we all have a lot on our minds, and online privacy probably isn't one of them. It's why I love Delete Me. Just let them take care of it for you. Have you ever heard the expression, if something is free, you're probably the product being sold? So join Delete Me and save 20% on all their plans with my code Ricky, linked in the description. Huge thanks to Delete Me and you. Now back to the show. Ultimately, this testing didn't happen. Allegedly, Stockton Rush got angry and irritated with the fact that they had all these hurdles to jump through and then just scrapped the idea altogether. The next thing is what they call their 4-kilometer data. This is testing that they extrapolated based on 1/3 scale models and going to certain depths and then extrapolating how it would affect the craft at the full 4,000 meters or so.
The DAR predicts failure to be hoop failure on the inner surface at the center of the cylinder at about 2.21 times the design pressure.
And in their testing, what they found is that the pressure on the hull, this here in between the 2 ports of titanium where it's held, the maximum deflection would happen right here in the middle. And around that area, they were seeing deflections 37% higher than they expected. Now that's always going to be troubling, and it was just another one of those things that didn't add up while they were doing this testing. Now this is on their earlier hulls during their testing and evaluation cycles back in 2018.
We hadn't really gone deep enough, long enough, and we were flexing 37% more. So it was the first warning.
Now, for something like this, it's really important to be able to do a visual inspection or any other kind of non-destructive testing before going out onto these expeditions. But part of that was a challenge because the outer casing is covered in basically like a rhino liner. It's a sort of tough and hardened outer shell to protect the carbon fiber on the outside. And on the inside, there's an inner liner. So one of the questions that Nissen was asked is, how easy was it to actually get in and how much of it could you actually see? And the answer was really not very much. It was only really close to the titanium rings where the carbon fiber was mated. So Nissen flies out to the Bahamas during this testing, verifies the crack and says, yeah, this hull can't be used. Now, OceanGate claimed that they were scrapping missions that year because of a loss of the support vessel, which was not true, but they were just trying to save face at that point. And then he was fired shortly after in June of 2019.
The optimum cycle life was 10,000 cycles to maximum rated depth, and the limit was 1,000 cycles to maximum rated depth of 6,000 meters. Do you believe the Titan Hull 1, before testing began, would have been able to withstand 1,000 cycles to depth?
No.
As you're aware, the Titan Hull 1 did not complete even 3 cycles to a shallower depth than 6,000 meters without having a crack in it. Where do you believe the gaps between the analysis and the real-time testing occurred?
It got hit by lightning. You would have thought that it would do better performance than that when you have a safety factor, like you just mentioned. That margin is huge.
Nissen even claims that the hull was struck by lightning while in the Bahamas, and that could have attributed to the crack and other issues. But that's not 100% verified.
I know your presentation says alleged. That is a difficult thing to prove, except I had to drag a lot of my engineering team down there to replace all the electronics in it, and I could find all the lightning traces.
Then there's the viewport. So on the front nose cone, there is a acrylic viewport, and Dr. Mush was very adamant that this be very visible, be big enough for a human head to fit into for maximum viewing. One of the red flags that we reported a year ago was that this viewport acrylic was only rated for about 1,300 meters, not 4,000.
Will said, I'll make it for you, but I'm only going to cert it to, I think it was 1,300 meters. Stockton said, fine. Neat thing about acrylic viewports is they do a very good job of telling you when they're failing.
You'll see crazing, which is like microvoids in the fibrils, and crack growth. And you can see that visually before it's too late, ideally. And he also mentioned concerns of cold flow or creep, which is a slow deformation in a material that is exposed to high stresses for a long period of time. And so this gets to one of the great challenges of engineering, which is at the interfaces. On the Titan submersible, we have a couple of different interfaces. First is the acrylic viewing port to the titanium dome. Then we have the titanium dome to the titanium ring to the carbon fiber hull. And that's kind of repeated on this side as well, if you could imagine. Those are the points where issues are going to be likely to happen. And the reason is because the modulus of elasticity, which is the stress over strain, meaning if I push on something really hard, how much does it shrink? Or if I pull on it, how much does it stretch, is different for different materials. So titanium and carbon fiber aren't going to be the same. Now let's say this is the carbon fiber here, and this is the titanium. And so this then would be the mating surface. That's where the glue is being adhered to. But if I pull or push on this titanium and carbon fiber separately, maybe the carbon fiber moves this much, but the titanium only moves this much. And so that means then that this glue surface is going to start to have some shear applied to it. And this happens over and over with every pressure and depressurization cycle. So that might have potentially been a cause of the issue. And it's not just the modulus of elasticity and other material properties. How about thermal expansion? When the Titan is up on the surface, it's being hit by the sun and it can get really hot. It could have components that are over 100 degrees Fahrenheit. And then in the deep oceans, it's really cold. So all different materials also increase, they shrink and grow at different rates based on temperature as well. They also mentioned that they went from grade 5 titanium to grade 3 titanium, which is very notoriously difficult to work with. Titanium is incredibly strong per unit of weight, which is what makes it so great for aviation and other applications like this. But grade 5 titanium, according to their reports, was going to be too expensive and take too long. Plus, the stronger the titanium, the harder it is to machine. So it's not just that the material costs more. Machining these parts is increasingly difficult. You need much more delicate machinery, harder bits, and everything else. Next up, there was questions about their monitoring methodology. Now, they had an acoustic system, as you can see here. They have this string of acoustic sensors about 120 degrees apart around the entire circumference of the hull. And the idea is that it was listening for what would sound like breaks. Imagine if I took a piece of metal or steel and bent it or broke it, that sound of fibers breaking, these mics would pick up and it would report. The idea was that if there was any kind of breaking or yield starting to happen in the carbon fiber, for example, they would be alerted and they could abandon the mission and surface. But that wouldn't matter if the catastrophic failure onset was instantaneous like it was in this case, right? It wouldn't matter if you got a little audible warning, you wouldn't be able to take action because the entire pressure vessel would implode, which is what happened.
My final question is, would you have felt comfortable as the director of engineering going down in the Titan submersible, specifically hull 1 to full rated depth?
That's almost the best question here, isn't it? Stockton's and my relationship started to turn sour. He wanted me to be the pilot that runs the Titanic missions. And I told him I'm not getting in it. And he asked me why. And I said, because the operations crew, I don't trust them. But I didn't make it any easier with the following question. He said, well, what if I'm mission director? I said, you still have the same operations group.
So these are different teams that work on different parts of the process. And he apparently didn't trust the operations team to really know what they were doing, to trust his life with it. And he also was very adamant that they used the word experimental in their waivers and made them put that in. That way people knew that you're getting on an experimental craft. This is not like flying on a Boeing 737 that's been in flight for 4 decades, right? This is new. So now let's talk about what we probably think happened exactly. So this video here is an animation, and we'll give credits to where this is from here in the description. But this animation shows that a failure is likely to have happened right here in the middle. And the reason is because that's where the maximum deflection is, right? If you pin the carbon fiber here and here, then right here in the middle would be where the maximum deflection would happen. So you might be wondering, why is that tail cone in such good shape? I kind of had that thought for a second. I mean, this is imploded like a tin can. It wouldn't look like that. Well, remember that this part isn't part of the pressure vessel. Only the carbon fiber hull and the 2 titanium domes on either side are. That was the part that was actually pressurized. This part would allow water in and it didn't have to hold back 5,500 PSI like the rest of it. So as a result, when this crumbled, this probably broke free and this set out on the bottom of the ocean floor, as we see here in the video. One of the early theories was that, this imploded from right in the middle. But if that were to be the case, then there'd be equal amounts of wreckage on either the aft and the forward parts. And that wasn't what happened. Also, another theory was that the acrylic front viewport had failed because, it wasn't rated for beyond 1,300 meters. But if that had happened, then you would have had a huge rush of water coming in, and it would have probably pushed out instead of imploded upon the vessel. But most likely it failed somewhere in the front. The carbon fiber to titanium ring component failed and started to crumble, and the failure propagated backward, and the front separated more quickly, and it all settled out in the bottom of the ocean, and the tail cone was the most intact. We do need to dwell on these things. I know this is a very uncomfortable story, that life was lost, but we as engineers, we learn from our mistakes. These kinds of mishap investigations are what brought us safe aviation. Many, many test pilots in aviation lost their lives over the years to various airframes. And then from each one of those failures, we figured something out. We've identified things, and then we build them into our standard operating procedure. Now, this is a frontier, and we're not going to stop doing it. Human beings love a good thrill. Now, would I ever get into a vessel and go visit the Titanic? No, I'll watch it on my computer. But for every one of me, there's also a person who would do that. And we already have the next generation of people doing this, right? We have the Triton 4000, which is the next level submersible being built by billionaires to do this exact mission. Now, they have a different design. It's much more of a sphere, less of a cylinder, and it only carries 2 people. But the point is, we're going to keep doing this, and we should learn from what we can and keep making things safer.
But I didn't trust Stockton either. They would take a look at where we started, and when I was hired, nothing that I got was the truth. I was held with a bag and trying to save, and I couldn't quit.
There's a long-standing engineering precedent of engineers, voicing concern and people saying, don't worry, it'll be fine. We'll just do it anyway, right? Like Challenger, for example, in the 1980s, when the company Morton Thiokol was in charge of some of the O-rings, and there was an engineer that kept saying, hey, we shouldn't do this. These O-rings don't really seal at lower temperatures. This morning at the launch site, it's colder than we thought it would be. Bad things can happen, and literally exactly that happened. So maybe the first lesson we can learn is let's listen to our engineers, especially when it's uncomfortable news. We have a lot more to go, but I think it's really important to remember that in engineering, we often learn from mistake. That's the only way. How else do you go from never having flown to going and flying? How do we go from dangerous treks to watch the Titanic wreckage to daily trips that are safe and have no rate of incidents? Well, through continued learning and humility, right? What we're doing here is incredibly unsafe. One of the comments in my previous video mentioned that for an airplane or a spacecraft to go from landing on Earth to outer space, they go from 1 atmosphere to 0, right? This is from 14 psi to 5,500 psi, like 300x the depth and pressures. So if you have any questions in particular, let me know. I can make little shorts or write-ups on our website and address them all. Don't forget to check out tubedavinci.com to see the full video, be a member, support the channel, and join our newsletter and everything else. So until next week, I'm Ricky Da Vinci. Thank you so much for watching.